Hello, I'm Phil, and I'm a PhD student in theoretical computer science, and today I'm here to talk to you about computing optimal flow decompositions for assembly. So, first, for the motivation, where does this problem come from? When you do assembly, you have short reads, and the problem is that you have ambiguity and you don't know which short reads correspond to which long sequence, and the goal is to recover these long sequences. And there are multiple ways to do this, but for both reference-based methods and de novo methods, you can end up with a splice graph. For example, for de novo methods, when you have a de Bruijn graph, you can contract the simple paths and then end up with such a network, which is in a perfect world, it's a directed acyclic graph, and you have nodes that are connected by edges, and each edge has the abundance value of this read. And the thing is, in a perfect world, it forms a flow network. And what is a flow network? You have these weights on these edges, and what holds is that for each node, the values that go into it are the same that go out of it. So at the beginning, you can see out of the S node, we have 1, 3, and 1 going out of it, and in the end, in the T node, it's the same values going in. And this holds for every node, that what goes in from the left comes out from the right. So the sum is always equal. But this only holds if you have a perfect read, which obviously is not the case in practice. But there are methods to smooth this network out so that you end up with a directed acyclic graph, and you have this flow property, which is called conservation of flow, that no flow gets lost. And now the goal is to get back the long sequence reads. And how do you do that? A sequence is then just in this network a path going from S to T, and obviously there are many ways to find such paths. So how do you know which path corresponds to what sequence? You want that the frequency of a sequence actually corresponds to what you have in the data. So you split it into the paths such that each path has a weight, which is then the frequency of the sequence, and you have that for each edge, the sum of the weights of these paths have to sum up to the flow value, which is the sequence of this short read. And now when you found such paths, each path corresponds then to a sequence. So in this example, you have 5 paths, and from that you could reconstruct your 5 sequences. And now with this formulation in place, we have a problem that a computer scientist can understand. And it looks like this. You have an input, which is a graph G, which is a directed acyclic graph, which has a unique source and sink node, denoted by S and T. A flow, which assigns to each edge a flow value, which again is the frequency of the read. And we have a positive integer k. And the problem is now to find an integral flow decomposition, which is a set of such paths where each path has a weight. The weights don't have to be unique. You can, of course, have paths that have the same weight. And we want to use at most k paths. So this is the problem I want to focus on today. And of course, the question is, how do we choose k? This is not obvious, but under the paradigm of parsimony, we want to minimize it because this seems to be a reasonable assumption, and this is nothing that we invented. This is done before, and there are a wide variety of heuristics that try to solve this problem so that the k becomes minimal. Most notably, there's a greedy heuristic that just picks a path that it can assign the maximum weight and then just finds solutions greedily. And this has been implemented in toolchains such as Draft or StringTie. And recently, last year, there has been a new heuristic by Shower and Kingsford, which they called Catfish. And they did a huge set of experiments on a large data set that had over 4 million input graphs. And what they found is that their heuristic vastly outperforms the greedy heuristic that was before considered the best heuristic. And now I talked about heuristic. The question, of course, is why heuristic and why don't we solve this problem exactly? Just find the minimal k and the minimal decomposition. It was shown that this problem is NP-hard even if we restrict the weights to 1, 2, and 4. So this is a very hard problem to solve. And we can't hope for an efficient algorithm. And for this, I brought a quote from a biologist, Joseph Felsenstein, who said this in the 90s. About 10 years ago, some computer scientists came by and said they heard we have some really cool problems. They showed that the problems are NP-complete and went away. And I don't want to go away today, so I brought a friend with me, which is FPT Man, and he helps me solve NP-complete problems. But how does he do that? If a problem is NP-complete, then the best we can hope for is an exponential algorithm, and it can look like that the runtime is c to the n, which is here on the left. And now the n, in our case, would be the size of the input graph. And if we make the graph larger, then the runtime would become really, really slow. And this is obviously really bad, and we don't want to do that. There's a technique that's called fixed parameter tractable, where we want to look at the problem a bit more closely and encapsulate what makes the problem hard and pull the n out of that. In our case, it would be the k. So what if the problem is only hard if the solution is really large? And if we can find a small solution, then the runtime might not be as bad. So the runtime could look like, on the right side, d to the k times n. Now, even if the d is much larger than the c, if our k is really small, then the runtime might still be fast enough to use in practice because we are now linear in n, which is the size of our input graph. So we looked at the data that Shower and Kingsford used for their Catfish heuristic, and they have this publicly available. So if you want, you can download this. And what we found was that 99% of the instances there decompose into smaller than 8 paths. So it seems we could exploit the small natural parameter. And because there are around 4 million mostly small instances, we have to handle large throughput. So we want to be really fast in practice, not only in theory. And we want to output decompositions. We don't want to just check which is the optimal value of k. We want to get the solution out of there so we can reconstruct the sequences. So we designed an algorithm that we call Toboggan, and it runs in linear FPT time, and we proved that the runtime is that, and we proved that this is correct. So we have an algorithm that has a worst case runtime that is linear in n, and we can guarantee an optimal solution. So we can guarantee you our tool that we have always finds the minimal number of paths to this problem. And this now gives us the opportunity to validate the model. We can look at the data that is there and see if the optimal solution that we found, that we know to be optimal, is actually what is there in the ground truth, to see if the assumption and the whole model with the flow network is a good way to model the sequence assembly problem. And we show that in experiments that our runtime is competitive with the current state-of-the-art heuristic, which is the Catfish heuristic. And we believe that this algorithm is usable in practice. So now briefly about the implementation and then to the experiments. The code is available publicly at GitHub. Just go to theory and practice/Toboggan. You can download it and run it yourself on the data, which is also available, and we implemented it in Python. So for our experimental setup, we took the data, which is simulated sequencing data for human mouth and zebrafish, and it contains the ground truth. So it's artificial data. It's not, doesn't come from real reads. So this then gives the opportunity to check if what the algorithm puts out is actually the ground truth. And we did a small deviation from their original setup. We left out the trivial instances, which were just graphs that consist of a single path, because our pre-processing just finds a solution there instantly, and it would not be interesting to include it in the results. So this removes about 64% of the data set, but we still have around 1.4 million graphs. And we run that on a dedicated system with an Intel i7 processor, which had 32 gigabyte RAM. And here are plots for our execution time. You can see that for the vast majority of data that we run in the milliseconds for each input graph. And if you look at it, for a lot of the data, we are faster even than the catfish heuristic. Our median runtime was 1.24 milliseconds against their 3.47 milliseconds. But this comes at a price because their variance is really small. They can guarantee you that their heuristic always runs really fast. But we had some hard instances, as you can see on the right. There is where we zoomed in a bit. So you can see that we had some instances where we took longer than 200, 400, or even 800 seconds. So if you want to use it in practice, you would probably want to implement a timeout. And if the execution takes way too long, then time out our algorithm and default back to another one as a backup solution. Because we solved the problem exactly, and the problem is NP-hard, sometimes the instance might be really hard to solve. But as you can see, at least in this data set, this didn't happen very often. And now to the ground truth validation. As I said before, we output the optimal solution, and we can look at the ground truth and now check how often the ground truth actually corresponds to minimal flow decomposition. And it turns out the majority of times it actually was a minimal flow decomposition. So for all data sets, it was over 99%. And the variation among the data sets isn't very large. So we believe that this model is a good model to model this problem, because most of the time it actually was a minimal flow decomposition. And for the exact recovery, here's a comparison between our algorithm and the catfish heuristic. What is the ratio of when we recovered the ground truth and outputted the correct solution for this assembly problem and not for the flow decomposition problem. And you can see that we have comparable performance. In some cases, we have the better performance, sometimes they, but it's always really close. So it's hard to say who's better here. So overall, we were a little bit better, but I think the takeaway from that is that this also is a good way to recover the ground truth. And when we didn't find the ground truth, and when the catfish heuristic also didn't find the ground truth, we looked at the Jaccard index, so the distance to the ground truth, and we can see that they look really similar, so that there seems to be the same amount of information missing for both algorithms to recover the ground truth that might not be covered by the flow network. So now I want to talk to you a bit about the idea of the algorithm, because I hopefully convince you that this is a good way to solve this problem. We have this flow network as an input, which is a directed acyclic graph. And for each directed acyclic graph, we can do a topological ordering, which is an ordering about on the nodes of the graph, such that each edge goes only from left to right. And then we want to traverse the graph from left to right and route the flow through that. So, for example, we can start and have the blue and the yellow flow both on the first edge and the teal flow going over the edge above that with weight 3. And when we do that, we get a set of constraints. So we now know that the blue and the yellow flow have to sum up to 3, their weights, because we know that the sum of the weights of the path have to sum up to the flow value on the edge. The teal flow has to have weight 3, and the yellow flow has the weight 2. And we can then continue, but we of course have to be careful how we continue. It has to be, of course, consistent. We couldn't just have the teal flow go through the other edge that is at the bottom with weight 1, because that wouldn't make sense. So we have to put the yellow and the teal flow on the same edge, and we can have a new pink flow above, and the blue flow can go below. And this now gives us a new set of constraints. And when we do it in that fashion, we always get new constraints, and we have a linear system where we have a matrix that has the indices what flows go over which edge. We have a weight vector, which is contains the weights of the flows that we want to, of the path, ST path we want to find. And on the right-hand side, we have flow values. And now we can solve this problem by dynamic programming. We go from left to right and build our linear system. And of course, we have to make choices sometimes. So there are multiple values to continue the flow, but we explore all of them in a search tree in the dynamic programming. And of course, sometimes we can abort early because the linear system is inconsistent, and in the end, we can just look through all systems in memory and look if there is an optimal solution, and then, for example, via backtracking, you could find the decomposition into the paths. So in conclusion, we have an algorithm that has a theoretical worst-case runtime linear in N. We have competitive runtime with heuristics. We can guarantee that we find the optimal, that is minimal value of K. And our Python implementation seems to be very fast already, so maybe implementing it in C++ could be even faster. We have a paper on that, which is available on arXiv, and the code is available on GitHub. So I want to thank you for your attention, and I want to thank all of my co-authors, especially Blair Sullivan, which is also here with me at the conference, and who invited me to her lab to work on this problem. Thank you.
Thank you, Philipp. Are there questions, please?
Thank you. It's very nice work. So I was wondering if you have any idea, or if you've looked at how sort of the uneven coverage that is characteristic in RNA-seq data might affect this algorithm. Because, you know, sort of one problem is that the flow decomposition problem, with some level of noise even, is how we're modeling it, but you know, certain data sets, certain assays can produce very uneven coverage. And so I know, for example, that in string tie, there's this lossy flow approach that allows you to sort of gain or lose mass as you traverse edges. So I guess the question would be, have you considered that, and what kind of changes might be possible to allow that in this framework?
Yeah, thank you for your question. Of course, this assumes a perfect world where the flow is correct, and we approach it from this standpoint at the moment, that this is our input. So, but like you said, of course, it would be interesting further research how such an algorithm can be modeled or changed in a way to also work with data that is less perfect, so to say.
Thank you.
Okay, any additional questions? Okay, so then let's thank the speaker.
One sec.
Yes.
Not a question, but I just want to say this was
Oh,
a
there. I see.
beautifully structured talk and so clear.
Thank you very much.
Okay, great. So let's thank the speaker again.